So here's our example that we want to go over. It's 2.4. Now, it's important here, oops, sorry about that. It's important here that we go in and we actually draw a good picture. I think it's super, super important. So what I'm going to do here is that the first thing that I want to do here is it says you have a model rocket that's fired vertically from the ground and ascends with a constant vertical acceleration of 4 meters per second every second for 6 seconds. Then the fuel is exhausted. So that means there's a period of time where it's not in free fall. Free fall means that it's only under the acceleration due to gravity. So let's look at this here. Draw motion and then plot y versus vy. And then let's see, how do I set this up here? So let's look at this thing here. So the first thing I want to do is that for 6 seconds, it's being accelerated. After 6 seconds, there's no more thrust from the rocket, so now it's in free fall. So what I'm thinking here, depends on how you look at this thing here, I'm going to break this up into 3 intervals. Do I have to do this? No. I could break it down into 2 intervals, but I'm going to break it up into 3 intervals so it's easier to understand what's going on. So here I go. So my first interval implies that I have rocket fuel. Which then gives an acceleration, which I'm going to call my interval 1, of 4 meters per second squared. And then, because they ask maximum height, you're going to see that I'm going to do 2 and interval 3. And then here, it's now in free fall. Free fall implies that acceleration 2 and acceleration 3 are then minus g. So how do I draw this picture here? Well, I imagine that I'm at ground level. Okay, in other words, I'm going to set this guy equal to 0 here. So now I have a rocket. This rocket is at ground level, and what it does here is it now has the thrust. So as it has this thrust, it's going to go up some height, right? It's going to go up to some height right here, and at this height, the rocket has now no more thrust here. So now this rocket here is in free fall. So what I'm imagining here is that this is interval number 1, right? The rocket is going to go up to some height here. And then when it gets to this point right here, it then reaches maximum height. What do I know about maximum height? Maximum height tells me that the speed is 0 here. So I'm going to call this interval 2. And then the rocket now starts to fall back down. And then it's going to come all the way down to here, where at some point, it's right before it hits the ground, it's going to be moving some speed here. So what do I know about this? Well, for starters here, I know that this has some acceleration 1, which is some acceleration 1, which is going in the positive direction. And then I have free fall that starts to occur. This is the acceleration due to gravity here, and then down here, this is the acceleration due to gravity right there. which we already know is minus g here. So does that make sense here? I think that makes sense here. So what I want to do now is that when I look at this thing here, what does my motion diagram mean here? Well, my motion diagram here tells me that, remember, I don't have to give all these details. What I do know is that the initial velocity is 0. And when I get to this point here, I'm going to call that V2. And then when I get all the way up to the top, I'm going to call that V3. So I know that this is V3 right here. And then when it's coming down here, this is going to be some V4. So what do I know about this thing? They're asking what is the maximum altitude. So when I look at the maximum altitude, what I really mean here is that the distance between here and here, I'm going to call delta y1. The distance between here and here, I'm going to call delta y2. So if I want maximum altitude, ooh, that doesn't look right. This guy, which I'll call y max, should be delta y1 plus delta y2. Okay, so then what else do I need to know here? I think that's it. So the next thing that it says here, let's plot y and velocity here. So here I go. So let me see if I can do a good plot. It's the y one that's going to be the most trickiest one. So here's my y, here's my vy, and here's my ay. So what does the rocket do during the first interval? Well, during the first interval, it's going to speed up. So here I go. So if it's speeding up, that means I must have a curve like this. So let's go look at that interval. So if I'm speeding up because of the thrust, let's see if I don't screw up my curve like I did last time. Then I know that my acceleration must be what? Be linear. And the reason why it's linear is because I have an acceleration like this. So this is my acceleration 1. I know that right here, I know that that's v equal to 0. This point is v2. And I'll leave it right there. So then what happens next? I'm now in free fall. As I'm in free fall, I'm decelerating. So let's draw the first curve here. By the way, I should be careful here. I should call this interval number 1. So now my curve changes where I have to do what? At some point, I have to come in and I got to do what? I got to stop. Excuse me. And then what you're seeing here, at this point, I'm trying to show that the slope at that point is 0. So if I look at this and if I drew this correctly, I know that my slope here is 0, which is what I call V3. So if I look at this thing, my curve then should be what? Oops, wrong color. Let's do the green. Should be right there. It should stop right there. And then my acceleration, now note, if that's half a square, then this is about twice that. So this is A2, which is of course minus G. And then what happens? The rocket starts to speed up here. So as it starts to speed up, what this is saying here is that this guy's going to come and it's going to go faster and faster and faster. So the slope there has to be steeper, which means that this guy has to be, ooh, it's not, I'm gonna change this a little bit. Let's see here. So this thing goes further, further, and it gets steeper right there. So then I'm trying to make this more than one square. Is it more than one square? I'll make it. There's my velocity, right? And then right here is where it hits the ground. And then right here, you could see that at this point, this is where V4. And then right here is V3. But the acceleration doesn't change. It's a uniform acceleration. So then this A3 is still minus G.
Hey,
Okay?
Carlos.
Yeah.
So I'm looking at the green line that you have for, or I guess the second interval.
Yes.
And if we're looking at the velocity, if it already has a negative acceleration, wouldn't it be a negative velocity?
No, it's
No?
still going straight up.
Oh,
Because
so you're saying
it's still going in the positive direction.
okay, so like it's momentum, right? The momentum left over from the
No,
acceleration.
it's just the velocity that it was going at the moment that the thrust gave out.
Okay. Okay, cool.
Okay. So then I think I got everything here, right? I got everything. So here I go. I want to go calculate maximum height. So let me make sure I read the question right. Right? I got that. Let's go calculate the maximum height. So here I go. B, right? We want max height. So here I go. So what I'm going to do here is I'm going to set up two data tables, right? Here's the interval 1. Tells me that I have delta y1. I got a1. I got v2. I got v1. And I got t1. So when I look at this thing here, something that I did not put in, they also told us that the time from here to here was 6 seconds. Is that right? I think that's what they told us. Yeah, it's 6 seconds. So I know what T1 is. So then I'm just going to go right off my thing here. So what do I know? I know this is 6 seconds. I know it starts off initially at 0. I know that the acceleration is 4 meters per second squared. And then our big thing here is this. So I don't have what the final velocity is. So here's my table. So right away, you could see that I could go in and I could calculate what the first height is. But let's keep going because we're trying to set this up for that. So if I go to this guy here, what do I see here? Well, I have a table that now looks like this. I have acceleration 2, velocity 3, v2, and t2. So what do I know about this thing here? Well, I think it's clear that we are trying to solve for that height. So what do I know? Well, I know that this is minus g. I know that the final speed is 0. Do I know v2? No. Do I have time? No. So what you're seeing here is that I have two unknowns here. But the one thing that we do know here is that look at the boundary between 1 and 2. The velocity that you have at the end of interval 1 is the initial velocity of interval 2. So that means that these two intervals, or excuse me, these two speeds, they're the same. So you could see here is that if I solve for delta y1, I could come back and solve for v2. and then I could plug it into here and I don't have to calculate the time. So let's go do that. So now what I'm going to do here is I want to go calculate delta y1, and then afterwards go get v2 because I'm going to need it for that thing here. Let's go get the, let me go grab the kinematics table. So here I go. So if I look at this here, immediately I'm going to go after the kinematics table. So what do I know about the kinematics table? Well, for starters here, you could see I don't know v2, the final velocity. That tells me I got to use this equation right here. Okay, if I got to use that equation, let's go calculate that thing. So then that means I'm going here and I'm going to write, where is my mouse at? Right here. So then I'm going to go in, I'm going to start to calculate that. So this guy tells me right here that I must use, okay, here I go, delta y1. I'm going to put it into my notation. I have v1 t1 plus 1/2 a1 t1 squared. But note, v1 is 0. So that term disappears. So now I could just punch in my numbers to get this value. And so, of course, this means that this is going to be 1/2 4 meters per second squared times 6 seconds squared. And if my numbers are right, I should have 72 meters for delta y1. So right now, I have the first height. But remember, we need to solve for v2. So if I need to solve for v2, I'm then going to go in and actually, go get that. So, okay, so next, we solve for v2 for interval 2. Well, even if we didn't have the height here, if you ignore the height, I could just use the acceleration and the initial velocity and the time. So if you go to the first one, right, if I go into here, you'll see that I could use this relationship. Could I use other relationships? Yeah, this is assuming that I don't know what the distance is. So if I do that, then that means I have v2 equals to v1 plus a1 t1. Once again, what do I know? I know that this guy is 0, so it's just the acceleration times the time. So if I just go from the table values, this is going to be 4 meters per second squared times 6 seconds. And you could see this is 24 meters per second. And that's what v2 is. So now I have what v2 is. What am I going to do with that v2? I'm going to plug it into table 2 now. So here we go. So now what we want to do here is that we want to calculate delta y2 using our v2 calculation. So if I look at my table, this is what we were solving for. And now I'm going to plug in my value here. Now remember, this is minus g, v3 is 0. We now put in that v2 that we just calculated, which is 24 meters per second. So when I look at the time for that second interval, we don't know what that is. So you could see from the kinematics table, we don't know the time, which tells us there's only one equation, right? So if I come up here, let me change this to a different color. How about this pink here? Look at this. I don't know x. So that means I must use this equation. So let's go use that. So from the kinematics table, there's only one equation, which then says, I'm going to change it to my notation. It's going to be V3 squared, V2 squared plus 2A2 delta Y2. So now I got to go in and compute that. So what do I know? I know that V3 is, of course, 0. So you could see here is that I'm going to bring V2 squared over, but note that that's going to give it a negative value here. So now I'm going to solve for delta Y2. So if I bring that over, I'm going to get minus V2 squared. And then see, I got to divide by that quantity, which is minus 2A2. And this will be Y2. So here I go. So when I look at this thing, this is minus 24 meters per second squared quantity. And then this is going to be 2, but this is now minus 9.81 meters per second squared. And you could see that this minus sign and that minus sign cancel out. Assuming that my numbers are good, I'm going to get 29.4 meters for delta Y2. So now I have both heights, so I now know what my maximum height is here. So my maximum height then looks something like this here. So then the is, which will be this guy. So what did we calculate for the other one? I don't quite
Hey,
remember.
Carlos.
Yeah?
Are you going to be picky about us carrying our units throughout our calculations?
Not if they're reasonable.
Okay.
I mean, if yeah, by the way, one of my pet peeves, if you're putting in like 10 significant figures from your calculator, you know, I'd call you a liar because there's no way you could know that thing to that many sig figs. If you're off by 1 or 2 and then round off at the end, I'm good with that. So if I look at this, I don't know what the value that I got for the other one is. 72 meters. So I have 72 plus this 29.4. That should give me, what is that number? I think that's 101.
Yeah, it's 101.
So this is 101 meters if I approximate this thing. And if you're going to do the two sig figs, this would be 100 meters, or this is 1 sig fig, but it's 2 for the way we're looking at it. So then this would be our maximum height. So one of the things that you're seeing here is that right at the end is when I'm really thinking about this. Okay, so that ends that part here. You know, I got to go get the question because I don't remember the last part. So let me add the question here again. So now we're asking the question, what is the total elapsed time from takeoff until it strikes the ground? Now, it turns out that there's 2 ways to actually do this. And how you see it really depends on you here. Let me show you the most common way that people do it. So what we're interested in here is that what we're really trying to do, we want the total time. So if you want the total time, so it says the most common way is to calculate 3 time intervals. And according to what we said here is that the total time of flight, according to what we drew, would be these 3 times here. So when you're looking at this thing here, note that this guy was given. This guy we calculated. Excuse me. So what did we get when we calculated that? Did we calculate it for time 2? No, we didn't calculate the time 2. So I thought we had calculated, so that means that this guy and this guy are not calculated. And so what this implies here is that you need to do, multiple calculations. But what I want to do here is that I want to look at an alternative here. And the alternative here is that there's a completely different picture that we can do. Okay? And I think that's what I really want to do here. Because I think this is very, very instructive. But doing it this way requires a quadratic equation. Okay, so here's what we want to do here. So the first thing is that so this is my preferred way, and so this is the second way. I just realized I said the most come way, or maybe the most common way. My brain always works faster than my hand, of course, as you've already can tell. The second way to solve this time is by noting the following here. So if I draw my interval, and what I said earlier is that, remember, there's really only 2 intervals. And how do we identify intervals? We identify intervals by constant acceleration. So you can see here at some point, the rocket turns off right here. And so when you're seeing it, we have one acceleration, right? And that's what we called interval 1. And then there's this point here. There's this acceleration, which we already know is minus g here. Now, to not mix up intervals 2 and 3, I'm going to call this interval 4 now. And what do I mean by interval 4? Because in interval 4, the rocket does what? Well, here we know that there's the thrust. Now there's no thrust. The rocket goes up, hits the top, and then it comes all the way back down. And what you're seeing in this case here, so when I'm looking at my rocket, it's only experiencing the force of gravity, the acceleration due to gravity, in such a way that it now has some high final speed, which I called V4 before, which I'll stick to here. So there's really 2 acceleration intervals. And so once again, to give you a sense of what I'm talking about, look at our graphs. There's 2 accelerations. So that means I should be able to solve this problem without looking at 2 and 3 here. So here's the thing so in this case here, if I look at the total time, I have T1, and then this whole interval I'm going to call 4, and I have T4. So we know this guy already. We already said that's 6 seconds. So this is what we want to calculate. This is our unknown time that we want to compute here. let's set up a table. So the table that I want to set up is for interval 4. So the data table for interval number 4 should look something like this. There's delta y4, a4, v4. Now note that that's the initial speed right here. And then finally, here's t4. So let's look at this thing. Well, clearly what we want to do here is that we want to solve for this guy right here. We need that T4. Well, do I know what V2 is? Absolutely. We computed that earlier. This is 24 meters per second. Do we know the final velocity right before it hits the ground? The answer is no. We do not know this. Do we know the acceleration? Yes, we do. We know that it's minus g. But wait a minute. Do we know the height that the rocket actually fell? And the answer is yes. So the thing about it, where is the initial height of the rocket? So let's go look at this distance here. The initial height of rocket in interval number 4 is what? It's at where? Look at that. The initial height was delta y1, right? We know what that height is delta y1. And when we calculated it, we said it was 72 meters. So this thing starts off at 72 meters. What's the final height of the rocket? Note, this does not include the maximum. The final height of the rocket is what? 0. So when I look at delta y4, note, my final is 0. My initial is 72, so it's minus 72 meters. So I know that height change. And note it's negative because why? It's going in the negative direction. That's the displacement. So once again, this tells us the equation. So if that tells us the equation, I could then go in and I could go back to the kinematics table here. So if I go grab that kinematics table again and copy it into here, here I go. And you could see that the kinematics table says the one thing that I don't know, which is the final velocity, is this equation right here. Okay, it's that equation. So let's plug that in. So what do I have here? That means that I have delta y4 is equal to what? The initial speed. What's the initial speed? It's v2 times t4 plus 1/2 the acceleration of this interval times t4 squared. And what you're seeing here is that this technique is a little bit more complicated because it requires the quadratic equation that you got to solve for. Let's put in our numbers and let's go solve this thing. Now you can do this again one of two ways, but I'm going to set up this equation. So let's do this. So mathematically, it's 72. This is going to be what? 24 T4 plus 1/2 minus 9.81 times T squared. And if I clean this up a little bit, I'm then going to write 1/2 9.8 T squared to the 4th. I'm going to bring, since I have two negative signs, I'm going to clean this up. So I'm going to get what? Minus 24 t to the fourth and minus 72. I'm pretty sure that signs look good to me. But again, you should never trust me. So what I'm going to do here is that I'm going to solve for this problem here. And what you're seeing here is that if I solve for this, T4 is, when I look at this, T4 has two solutions. But only one of them makes sense here, because if I have the trajectory that goes like this, the trajectory is this later time. The other time would be right here, but that's not what we want. We want this time all the way up to there, which is T4. So when you solve for that T4, you're going to get that T4 in this case turns out to be 7 seconds. So solving this equation gives you 7 seconds. So then the total time of flight will then be T1 plus T4, which then gives you 6 plus 7, which gives you 13 seconds for the total time. And that solves that question right there. Okay. Any questions before I move on here?
Hey, Carlos.
Yes.
I am a little bit confused on why the delta Y4 is negative 72 meters. I think someone else asked it in the chat, said that it would be the maximum height.
I missed that. I did not. You know, if you say something in the chat and I don't respond, just give me a holler. Don't let me not answer questions. I prefer that we actually talk. So let's go answer your question right here. So the first thing that I'd ask you to think about here is that, does this argument right here make sense to you? Because when I think about this here, it's really what? The final minus the initial height. I started off at 72 meters. I ended up at 0, so it's got to be negative. But that's not really answering the question.
If it's final minus initial and you start at 0, why wouldn't
No, you do not start at 0. You start at this height right here.
Oh, right, yeah, okay.
72 meters. You end at 0. So this Y4 is 0 right there. So the difference tells you that it must be 72 meters.
Wait, was the question asking what's the total amount of time elapsed from the moment that it stops?
From when it starts to when it ends.
Oh, like from the very beginning?
Yeah, the total time that it's in the air. And so,
wait,
yes.
So why? I'm sorry.
Isn't the max height 100 and what is it? 101 meters, not 72? Isn't 72 just the from when it stops propelling, and then it keeps rising? So there's more height to it, and it's still going, and then it starts to drop.
Okay, but that doesn't tell me about the height change of the rocket. The height change of the rocket is negative 72 meters. If it starts off at 72 meters and it ends at 0, that is a negative change.
But doesn't the rocket at the very beginning start off at y=0 as it does in the picture?
Mm-hmm. Yeah, I agree.
So then it goes 72 meters, but then once it stops propelling, it goes the other, was it
Here,
29.4 meters?
let's go back to the picture. So what you're finding here is that if something moves because of our sign convention, anything that goes up, that means that that height change is positive. Anything that comes down, that height change is negative. And I want to remind you that delta y, it's the displacement or the change in position from one location to the next. So when you're looking at this thing, and what we're asking here is that we're trying to calculate the total time. So the total time what I said, you can calculate this thing two different ways. I could calculate it this way, or I could calculate it this way. And what I said here is that this was the most common. But there are many situations where this is the easier way. And so this way right here was the one that I wanted to focus on, because I wanted to deal with the situation where I have a rocket. Here's my rocket. How much time does it get to this height right here? And what we said was that this amount of time from here to here, we called T1, which we knew was 6 seconds. Now, the issue at hand here is the question, excuse me. So the issue at hand here, this goes all the way up and it comes all the way down. And so we could see here that this thing starts off at 72 meters. And yes, it goes up to 101 meters, but in this calculation, that is irrelevant. All we could do is talk about when we start and when we end. And this final height here is 0. Displacement is about its starting point and its ending point. And as far as what we care about, this is the change in height of the rocket. I don't care whether it's going up. The fact is that we will account for it going up higher because look what we did. We accounted because we said that the initial speed at this point was what? 24 meters per second. But in the end, look what happens. When it gets to this point, it is still moving 24 meters per second in the negative direction. So I could have also solved this problem by saying that this thing moves 72 meters per second. My acceleration is minus g. This final speed we don't know. And this initial speed could have been 24 meters per second because it's now pointing the negative direction. I could have gone and solved for that problem right there. And you know what you would have gotten? You would have gotten 7 seconds again. So the fact is, all we care about is the height change. We only care about the endpoints. And that's why we get that same type of thing.